This week we are going to complete the introductory chapters, this one on complexity. And then after this one, there's another lecture, which is a short one about modeling. I think I'll be able to complete both of these by tomorrow. And I think if time permits tomorrow, we're going to start with the remaining two important subjects. The first one is hard operational research. So we're going to discuss the methodology of systems thinking as it is applied to hard problems. And that will take some time. And we shall see an application. Following that, the remaining part, I don't know how many weeks will remain, but all the remainder of the semester will be devoted to soft systems and soft OR. So going back to complexity, we discussed the relevance of chaos and thermodynamics on complex systems. And assuming that we understood all those aspects, we are summarizing the properties or the attributes of complex systems as they are explained in Baranger's paper. This is a very good explanation of complexity. There are several attributes, I think 6 attributes listed, and the first 4 were these. And we now know that complex systems are similar to the general systems that we are interested in, having many constituents, these parts being interdependent, exhibiting several scales, and these scales at the lower levels produce an attribute at a higher level, which we call an emergent property or emergent behavior. We have discussed emergence and given examples of emergence. Property number 5 is that chaos and non-chaos occurs simultaneously in systems, depending on at which scale we are viewing the system. Now, there are 2 or 3 more relevant concepts which are not discussed in the Baranger paper, but we know from our previous discussions. These are adaptation and evolution. The adaptation, as you should remember from Akoff's discussion, is learning when the environment changes, when conditions in the external environment change. Learning takes the form of adapting to new conditions. Two-way interaction between the system and the environment results in adaptation or learning under changing conditions. For example, the stock market players acting on local information. You know that the theory of free markets, and part of which is called the stock market, tells us that agents, economic agents, investors, when they invest money in the stock market, they look at local information because they cannot actually handle perfect information about the stock market. Nobody is capable of obtaining perfect information about the stock market. And even if this sort of information were made available to an agent, to an economic agent, this agent would not be able to absorb all this amount of information. This is called Simon's bounded rationality principle. Herbert Simon is an important person who is active in operational research and also in computer science and even in economics. He received the Nobel Prize in economics in, I don't remember very well, 1980, 81 perhaps. And he's still teaching in America. So his theory, Simon's bounded rationality, tells us that even though theoretically we assume that a decision maker makes a rational decision using all the information available to him, and this all the information being available is sometimes called decision making under certainty, with complete information. In practice, of course, this is not possible because an individual person is not capable of absorbing, well, first obtaining, and then even if he or she is able to obtain it, of making use of complete information. His or her rationality is bounded or is limited. So individuals are unable to forecast the higher level consequences of their actions, and so they optimize locally. So when you are investing in the stock market, you are not going to be able to predict all the results of your actions in the future, but you just act on local information, which may turn out to be, for example, 4 or 5 alternatives in which you can put your money. And these alternatives have some attributes, desirable or undesirable. You look and examine those attributes and then make your decision. This is how the stock market works. But even if individuals in free markets are limited by local information and act locally, when you take them all together at a higher level, there is an emergent logic of their actions. This is the theory of free markets, you see. It is the dominant theory in economics in the world, as you know. In almost all countries except a few, governments are trying to implement market policies in managing their economies. And the scientific or the philosophical underpinning of pursuing such policies is this one. It says that the market is a complex system. At the lower level, it involves millions and millions of individuals acting in the market, buying or selling something, taking part in market transactions. And when they take part in transactions, in such transactions, they use only local and limited information. But then, if you view the entire market from a higher level, the market acts logically and rationally. There is a logic. This idea of the market acting as if it is proceeding according to a plan, even when there is no plan, is called what? What's the popular term that tries to explain this? What's the name of the market, popular name for the market mechanism which produces this emergent behavior at the higher level? It's called the invisible hand of the market, right? Adam Smith first articulated this hundreds of years ago. We say that the invisible hand of the market determines the optimal allocation of resources. I mean, if you believe this story, of course. It's just a theoretical construct. You shouldn't really take it seriously and assume that it really applies in the real world. There are many, many situations in which this doesn't work. But anyway, as a construct, the market is a complex system like this one, capable of adaptation. It's similar to fish swimming, or to a flock of birds flying. Birds fly all together, but they change direction altogether. You have seen this in the spring, in spring skies usually. Birds fly in this way. And similarly, fish in shoals, when fish swim, they again act together. Each individual fish actually is acting on local information. Maybe the fish is able to sense or see only whoever is swimming around that fish. But then this local information results in an emergent behavior which is coherent, which is actually beautiful. Okay, so that's adaptation. And evolution occurs as a result of collective adaptation over generations. So these two concepts are also relevant to complexity. The final attribute of complexity, according to Beranger, is that it involves an interplay between cooperation and competition. So we observe competition in complex systems. In the market, for example, firms compete with each other. They try to take, they try to obtain some sort of advantage over the others. We call this competitive advantage. the entire objective of business strategy is to obtain and retain competitive advantage. So there is competition, we know that. But there's also cooperation. This idea of cooperation occurring at the same time as competition takes place is rather new, and it's very, very important. Taking the example of firms again, although they compete with each other in markets, they also cooperate and act collectively, for example, to prevent government intervention in markets. As you know, under capitalism, the free market system, or whatever, free or non-free, the market system, firms try to maximize their profits, and then they don't like regulation by the government. They try to obstruct government's intervention in the markets. You can see this every day. The exhibition of this sort of behavior is always in the news, on the TV every day. You hear about it. So they cooperate together for the sake of capitalism, but then they compete with each other in the markets. So this takes place. At the same time, this idea of firms, competing firms, also cooperating is very, very important in recent economics. Since maybe the last 30 years or so, the idea of cooperation of rivals, these firms are rivals of each other, but still they cooperate, is called, for example, it can be seen in many different formats. Does anybody know one format where firms cooperate? What is it? I can't hear it. No, not oligopolies. Oligopolistic structures are competition structures. It's called clusters, for example. Have you heard of clusters? Or networks, clusters, networks. We have courses taught in our department in the graduate courses about clusters and networks. These are extremely important formations. These have become more important with the recent policies of the European Union. For example, the European Union puts in a lot of money for firms in order for them to form clusters so that they can compete with each other. For example, the most famous clusters first appeared in Italy, in the region of, what's this historical city? Florence, and in other regions, shoemakers, companies which produce these Italian shoes, world famous shoes, have become successful in international markets because they cooperate and they form clusters. So competition or cooperation is as important as competition in understanding complex systems. Now, one final aspect, topic in complexity is how can we measure complexity? How can we, for example, assess whether a system is more complex than another system? So this is obviously an important question, and there are different ways of trying to measure complexity. We are not going to be interested in measures of complexity in OR. But as a concept, we should understand it. For example, the degree of complexity can be measured in terms of structural aspects, the complexity of structure. Structure, as you know, are aspects which change slowly. If there is a multitude of structures in a system, we can call it's more complex. It can also be measured in terms of function. A mathematical measure of complexity, this one is important as a piece of general knowledge, and also it's important in our other courses on optimization theory. In optimization theory, we have some, I don't know if you are still teaching it, some courses on, for example, combinatorial optimization, where you have a complex problem. There are measures of optimization problems in terms of complexity. Some problems are complex. When we say an optimization problem is complex, then you should understand that the computer will find it hard to obtain a solution when an algorithm is applied. Such algorithms are usually classed in two groups. Does anybody know these two groups? In one group, we have problems, or associated with these problems, we have algorithms which are reasonably easily capable of obtaining a solution. In the other group of problems, even if you have superly fast computers that do not yet exist, the problems are difficult or impossible to solve. Does anybody know the names of these two groups? The time for a computer to reach a solution can be measured in terms of the size of the problem, where the size of the problem, for example, can be measured in terms of the number of decision variables or in terms of the number of constraints. Or it can be measured in terms of the number of memory bytes that are needed to store the information. For example, in the LP case, it is the C, the coefficient matrix, the cost matrix, or vector, the A matrix, the coefficients matrix, and the right-hand side vector called B. If you store the matrix A and the vector C and B in the computer, it will occupy an amount of string of memory composed of, say, n bytes or n bits. Okay? This could be, for example, the size of the problem. If the time it takes the computer to reach a solution must be a function of this n, right? It must be a function of this n, the size. If it is a polynomial function of n, like, for example, n squared, or n cubed minus n squared plus 2n, something like that, a polynomial function of n, the problem is easy to solve. What would the time be a function of n if it were not easy? What sort of?
2 to the power of n.
Yeah, exponential, as our friend comments, as pointed out. If it's an exponential, if the n appears in the exponent, all right, then we say that it takes an exponentially long time for the computer, for the algorithm to arrive at a solution. Such problems are difficult to solve. Just keep this in mind. Actually, such problems are called NP-hard, and such problems are impossible to solve, actually. Most of the integer programming problems that you try to solve are NP-hard. You are only able to solve small problems. A large problem is impossible to solve. It's impossible to solve in astronomical time. The number of iterations that it takes to the computer to reach a solution is more than the number of atoms in the universe, astronomical time. Anyway, so let's see how this measure is computed. The length of the binary string that can contain two messages is 1, as you know. 1 bit of memory, computer memory, can contain two messages, 0 or 1. The length of the binary string that can contain four messages is 2. If you have 2 bits, then it can store 0, 0, 0, 1, 1, 0, or 1, 1. So 4 messages are possible. For 8 messages, it is 3, etc. And the relation is like that. Log t, 8 is equal to 3. So the length of the binary string that can contain 8 messages is equal to the logarithm of 8 to the base 2. So for a complex system with k possible states, just remember the phase space of a complex system and the huge phase space. If there are k possible states in the phase space, then we need n bits of information where n must be log to the 2 of k. You are going to see, you will probably come across this logarithmic expression. That's why I wanted you to understand that. It's a measure of complexity. It's a measure in optimization theory. We call this sort of complexity. It's called what? Does anybody know? the obvious term for complexity in computation. It's called computational complexity, okay? There's a large theory of computational it's really advanced mathematics. It's a complicated theory. We teach parts of this theory in some courses on optimization. So in computational complexity, you come across this expression all the time. So we are not interested in computational complexity, obviously, only, but you can see that these ideas are related. These ideas originated in communication theory. Do you know the name of the scientist who constructed the theory of communication single-handedly on his own, just on his own? Does anybody know his name? In electrical engineering, everybody knows his name. His name was Shannon, Claude Shannon. Shannon's theory of communication, he introduced these concepts for the first time in the 1950s, I think. So that's the end of our discussion of concepts of complexity. Now we summarize and try to relate systems thinking and complexity. Why are we interested in complexity? Obviously, we are interested in systems thinking in this course, but the relation between complexity and systems thinking, although it should be obvious by now, let's just point out the connections once more. Many of the attributes that define complexity also define systems. Why? Well, actually, because we are interested in complex systems, not simple systems. The commonalities between systems thinking and complexity studies are strong. The superposition or the intersection of these two areas is a large intersection, especially because almost all human activity systems are complex. When we talk about human activity systems, etc., the ideas that you should remember immediately in order to better understand should be ideas of attractors, of entropy, increasing entropy, of dissipating gradients. Gradient dissipation is how nature reacts. Animate or inanimate, or living or not living. All matter reacts to gradients imposed on them by trying to dissipate those gradients. This is a very deep and fundamental understanding of behavior of the world, not only humans, but matter also. So the reason I spend so much time on entropy and all these concepts is because it is very important for you to understand these. The person in the street, or the prime minister, or the ministers, or the members of the parliament know nothing about these concepts. It is you who should know and understand reality, okay? A strong education is based on understanding and making use of the concepts of fundamental concepts of science. So you should all remember, it's not just something we defined in one part of a lecture, dissipative systems or entropy. And you should all collect them together in understanding. So all human activity systems are complex and they behave in the way Prigogine, for example, tried to explain in chemistry. It's not clear yet if the mathematical constructs and results, you see, there's a lot of mathematics in complexity theory. Of course, we did not look at that mathematics, but there are people and books that have been produced using mostly differential equations, etc., trying to generalize the attributes and the concepts of complexity in terms of mathematics. If we were interested in complexity because we are climate scientists, meteorologists, or biologists, for example, we should be looking at, or control engineers, for example, we should be looking at the mathematics. But in OR, we are not able to use the mathematics of complexity. So it's what we say here is that it's not clear yet if the mathematical constructs and results from complexity research can be directly applied to the study of socioeconomic or socio-technical human systems. Why? Why are we not clear about the applicability of mathematics to such systems, complexity mathematics? because these systems are even more complex than systems that accept the mathematics. Okay? These systems are the most complex. Originally, operational research searched for models and theories that could simplify the essence of the world so that we might capture a part of social reality for decision making. This is how OR started originally. OR knew that the world was complex, but it thought that it would be possible to take one piece of the world and simplify it in a model and obtain some wisdom from it for decision making. Of course, when OR was doing this, it knew that the world was complex, but the world also appeared to allow us to produce robust models that could be used in applications. You see, in the good old days, let's say, the good old days of OR, this is about the time of the 1960s and early 70s. In those times, people thought that OR would be able to solve all the problems of humanity. All the problems. Such a strong belief was embedded in OR. The people knew that the world was complex, but it also would allow us, how would a complex world allow you to construct simple models? Why? What's the underlying attribute of complexity that allows modeling? If it is too complex, then we shouldn't be able to model and understand it and use the model to understand the system. What is the attribute of complexity that allows you to model it?
There is a pattern.
Yeah, what's the name of the concept? Attractors, strange attractors. These attractors, if these attractors were not there, the Amazon River could freeze next winter. But we know that the Amazon River will not freeze. The climate in the Amazon River is complex, extremely complex. The butterfly effect, etc., originate by Lorentz from this example. But we also know that it will not freeze, so there is an attractor. The attractor is a state which is not stable, but which is not chaotic, in between. So this allows modeling. Of course, OR, when in the 1960s, wasn't aware of these attractors. I don't think it was, but anyway. But after from the middle of the 70s, towards the end of the 70s, it says, with the growing realization that complexity is more problematic to deal with than thought before. Complexity was understood to be really more difficult to handle, and that prediction appears to be getting out of reach. You see, modeling, etc., or understanding nature has the ultimate objective of making predictions about the future so that we can arrange our affairs accordingly. We can make our decisions accordingly. But gradually, slowly, OR understood that prediction would not be really possible, was getting out of reach. The concern of OR, therefore, since the late 70s, although industrial engineering departments are not very, very aware of this, maybe, in many countries or in many universities, the concern of OR has been moving away from solving well-defined problems. This is what we try to teach you in all those courses. There are well-defined problems, and we try to teach you how to solve them. But the concern is not this. You see, it is moving away from this towards structuring debate about a complex world. You understand debate. Debate, müzakere, tartışma. Structuring, a structured debate is a debate which doesn't take place in a coffee house. Yani kahvehane sohbetinin ötesinde. Structured debate. This is the ultimate aim of OR, really, because human problems do not have solutions. You remember the concepts of solution, resolution, absolution, and dissolution. I asked you a quiz question, so structuring debate. Many of the attributes of complex systems are therefore certainly shared by human activity systems. The fundamental generalizations about self-organization as explained by dissipative structures, and complex adaptive systems are especially relevant to OR. A complex adaptive system is a self-organizing system. It's a human system because it adapts to changing conditions. These are relevant to OR. Hence, an understanding of complexity can help us better understand human activity systems. So that's the end of our lecture on complexity. I hope that you have read my notes on complexity also. Just also make sure that you read the Baranger paper carefully. Not for the sake of pleasing me or getting a good mark in this, from this, good grades in this course, because I'm not going to force you too much about the details of complexity in examinations, etc. But just for your sake of understanding, all right? Please spend some good time on complexity. Now let us move over directly to, I think it's this one. Yes, lecture 5. This is a short lecture. I shall complete this by tomorrow at the latest, on modeling. Now, modeling, models, and diagrams also. Now, you know that most of your time spent in our department is spent on trying to construct models and solve them. These are mathematical models, always. Mathematical models, or modeling, is the strength of our profession. Our profession of ORIE depends on two legs, let's say. There are two foundations. One is the applicability of the techniques of mathematics, probability statistics and optimization theory to construct models coming from the real world, of parts of the real world. And the other foundation is systems thinking, which tells us how to use these. So models are fundamental to our profession. Of course, other engineering disciplines also make use of models, but not as extensively as we do. In industrial engineering, we cannot do anything really unless we have a model. Modeling is very, very important for us. Diagrams, you are familiar with several types of diagrams. When you are constructing models, diagrams can help you a lot. Unfortunately, in our department, our students are not very good at making use of diagrams. So we try to point out some types of diagrams and encourage the students to construct these diagrams. So this lecture, short lecture, is about these things: modeling, influence diagrams, flow charts, precedence charts, spray diagrams, etc. Now, you know what a model is. Several definitions have been given to you before. Actually, there are now here 1, 2, 3, 4, 5 definitions. Each new definition includes the previous one, so extended definitions. The final definition is the one at the end. But let's read them from the beginning. The underlined concepts in red are the additional concepts each definition introduces. The first definition tells us that a model is a representation of reality, but this representation must have some purpose, intended for some purpose, always. Whose purpose? The purpose of the investigator or the purpose of the inquirer, whoever is conducting the inquiry. It's a representation of reality intended to be of use to someone charged with managing or understanding that reality. So managing and understanding that reality is our purpose. A representation of reality intended to be of use to someone in understanding, changing, managing, and controlling that reality. So changing and controlling are added. Then we add the attribute that the model represents the reality as seen by the people who wish to use it to understand, to change, to manage, and to control that part of reality. So as seen by the people introduces what into the model? Introduces what? What's the attribute introduced by making it particular to the people who regard reality? Subjectivity, right? It is subjective. It's not objective. A model reproduces one person's view of reality. So the final definition, which is the most general, is this one. A model is an external and explicit representation of part of reality as seen by the people who wish to use it, to use the model, to understand, to change, to manage, and to control that part of reality. So this is a fair enough definition. It doesn't say that it's a mathematical model, but you implicitly understand that it must be a mathematical model. In architecture, for example, physical models can be used before you construct the building itself. Even in mechanical engineering, physical modeling is possible, but not in our case. What do you mean by external and explicit? Well, you see, some models are mental. You have a mental model. Huh? When I, for example, mentioned the term Olympic Games, you have a mental picture of the Olympic Games, which we can call a mental model of the Olympic Games in your mind, which might be different from a similar model in somebody else's thinking. But the models we are discussing are not mental models. Huh? They are external models. They are explicit. They are not implicitly understood, but they are explicit. Actually, they are, for example, mathematical models like an Excel diagram, an Excel chart. An Excel chart is some sort of a mathematical model, isn't it? So you can show it to other people. It reflects your own view, but it can be used to explain your understanding to someone else. Okay, so that's what we mean by a model. It's a tool for thinking, so it is best for you to understand a model as a tool. It's like a calculator. I like this analogy. Huh? This metaphor is useful. You have a calculator. You would like to, for example, allocate your budget when you are going shopping. Huh? You have a calculator, so you make some additions and subtractions, etc., to allocate your budget to your the shopping needs. A model is similar. It helps you to decide. It's a tool for thinking. Since it's mathematical, the calculator analogy is not a bad one. Now, of course, systems should come in for when we discuss modeling. We are clearly talking about system models. Here we have some components of a model. These components of a system model, as you will see, the ones shown in red, are also components of the system itself. We are familiar with all of these. But specifically for a model, we have these components of the system in the model. The system may have other components which we do not show in the model, as we shall see. So the first thing is that it should include a transformation process. Your model should indicate a transformation process, which are the activities of the system. And the system does something. It uses some inputs and produces some outputs. This we call the transformation. It should include the boundary, the narrow and the wider systems. I told you that one way of identifying the narrow system was what? What's one method of identifying the narrow system? Yeah, more generally than that. The model. The model is the model of the narrow system. The mathematical models you construct are models of the narrow system. Okay? That's the way. The wider system takes the output from your narrow system. It's the output of your model. And the inputs also come from the wider system. What you model, the mathematical model you construct, represents the narrow system. So the boundary should be known in order to identify the narrow. There are subsystems, as you know. There are processes and structures which should be represented in the system. What represents the processes and the structures are variables. The variables of the system will represent these. For example, the example I gave you for a structural variable could be the level of inventory, which you indicate by x sub t, for example. In week t, x indicates the level of inventory that we are keeping. And the change in inventory from t to t plus 1, for example, is the net addition or subtraction from the inventory, which should be a process variable, a fast changing. Or if your model is not discrete, if t is a continuous variable, then dx to dt, the time rate of change of inventory should be, the change in inventory could be a process variable, etc. Inputs, uncontrollable inputs, control inputs, decision and decision rules. So all inputs and rules should be outputs, etc. Outputs, again, can be desired, undesired, planned, unplanned. So these are the things that the model should specify. And also, one of the outputs will serve as a performance measure. One of the output could be profit. Then you should try to assess your activities by checking whether your profits are being maximized or not. This is a chart which might be used, so it's not too important. Which aspects of the system should be parts of your model? Now, there are two questions, as you can see. The vertical question says, does the aspect affect the system? There's an aspect. And we are trying to decide whether this aspect should be part of our model or not, and what part. So we put two questions. Does the aspect affect the system? And the horizontal, the one at the top question is the aspect affected by system variables or inputs? Let's assume that the aspect affects the system. The answer is yes. But is the aspect affected by the system of the variables? The answer is no. Then that aspect must be an input. It affects the system, but it is not affected by the system. So it must be an input. If the answer to this question is no, but the answer to the horizontal question is yes, then it must be an output. The output does not affect the system. No. But it is affected by the variables or the inputs of the system. So it's an output. If the answers to both questions is yes, then it must be a component or a relationship in the system. A component is indicated by either a structural variable or a process variable. A relationship is indicated by the connection between these variables. Okay? In terms of diagrams, for example, you might draw circles or squares in which you represent the variables, in which you write the variables representing processes or structures. And then these circles or rectangles are connected by arrows showing the relationships, which may imply that if the first variable does not change, the one at the end of the arrow does not change, etc. And if the answers to both questions are no, then that's irrelevant, and you do not represent that part of the system in your model. So this is such a chart might be useful. Now, this part is the most important part of this lecture. What are the attributes of models? What should they be like, good models? First, I will discuss these attributes of the models, and then I will also indicate how you can obtain such attributes. Let's start. Simple but complete. Huh? A model should be simple but complete. It should not be trivial or irrelevant, obviously. Now, why should it be simple? Because simple models are easier to understand, to evaluate, to work with, and most importantly, to communicate. Now, if you construct an LP model, for example, which is capable of finding from infinitely many feasible solutions the one which is the best by applying powerful optimization techniques, such a model may be difficult to communicate, that is, to explain to a person. This person might be the problem owner, for example, who has hired you, who has employed you to look into his problems, and explain to him that the solutions that you obtain from your LP model make sense and are relevant. But if you have an Excel chart instead of an LP model, in which a finite number of alternatives, like 5 alternatives, are evaluated and the best one is chosen, then it is better, more suitable, because the problem owner will probably be able to understand this. So simplicity helps communication, which is very important for your profession. If you are employed in some organization where you try to construct complicated models, mathematical models, probably your job will be difficult. If you are able to obtain similar results, similarly efficient and effective results using simpler models, you will be more successful, and your life will be easier. And they can be explained to problem users and owners. This helps to convince them to use the models as tools for thinking. For example, an Excel chart, a spreadsheet. These are fine. I mean, don't think that spreadsheets are naive or too simple to use. They are sometimes very useful. Even if users do not understand its inner workings properly, a model should be easy to manipulate. Let's assume that you have constructed an LP model, and it's difficult to explain to the users how the algorithm works by moving from one basic feasible solution to another basic feasible solution in the direction of steepest ascent, etc., so that the optimum is right in the end. It's difficult to explain all of these things. But if you write up an interface, a menu-driven system, for example, that the user can use by changing the data and obtaining different solutions under different scenarios, etc. So easy to manipulate, it should be easy to manipulate. Simplicity is associated with the concept of parsimony. Parsimony, tutumluluk gibi. I mean, minimality, some sort of parsimony. It is associated with a famous dictum by the 15th century or 16th century, I think 16th century philosopher Occam. It's called Occam's razor. Occam's razor is a very famous dictum principle, let's say, popularly understood in English-speaking countries. It says the fewest possible assumptions should be made in explaining a thing. And it's the principle of parsimony. Models should observe parsimony. They should not be more complicated than necessary. So how do you... Okay, so let's stop here and continue tomorrow.